Alright, so picking up where we left off, one thing that I forgot to mention at the end of the last video, I did want to tell you guys, so we did this example where we saw that we had a vertical asymptote at x equals 1 for this function in the integrand, and we found that by splitting it up, we got one piece that was divergent. Okay, one piece that gave us an infinitely large area, so we didn't even need to bother finding the other piece because we knew that it was still going to be divergent. But what I forgot to mention is my word of caution, which I mentioned up at the top of the problem, which was to make sure you take note of that asymptote, because if we had ignored the asymptote, then if we actually evaluated the integral, we would get the following. So we'd get the integral from 0 to 3, excuse me, the integral from 0 to 3 of dx over x minus 1 would give you ln of absolute value of x minus 1 from 0 to 3. So we would get ln of 2 minus ln of 1, which is ln of 2, which is incorrect. Okay, so we just have to be careful, because if you hadn't realized that this had the vertical asymptote in it, you would have just gone straight through and gotten an answer and then moved on, and your answer would actually be completely wrong. So just have to be mindful now that we're dealing with these types of improper integrals, that these are circumstances that can happen. Okay? So let's move on to the next topic here, and that is the comparison theorem. So this is going to be a way for us to evaluate integrals more indirectly. So suppose that f and g are continuous functions, with f being greater than or equal to g, which is greater than or equal to 0, for x greater than or equal to a. If the integral from a to infinity of f of x is convergent, then the integral from a to x, or a to infinity of g of x, is also convergent. And if the integral of g is divergent, then the integral of f must also be divergent. And the idea behind this, graphically, is, here's my curve g, here's my curve f, from a all the way off to infinity. If we're looking at it in terms of area, what this first one says is if the area under f converges, so if this whole area goes to a finite value, then certainly the area under g must also go to a finite value because it's smaller than the area that's under f. Okay, so we're kind of like shoehorning it in there. We're forcing it to be convergent because we're saying, well, this bigger function is convergent, so that means the smaller one has to be convergent too. And then by kind of the opposite argument, if the smaller one, if this area diverges, if this area is infinitely large, and this function f has more area underneath it, well, anything more than infinitely large is still infinite. So if the smaller one is divergent, the larger one must also be divergent. Okay, so that's the argument that we're making here for these integrals. So let's go ahead and look at an example. So show that the integral from 0 to infinity of e to the negative x squared dx is convergent. So if you're looking at this, the first thing that we should probably notice is we can't do this one as is. We cannot evaluate this integral directly. So we cannot evaluate this directly. So we don't have the tools to be able to integrate this as is. So we're going to have to come up with a little bit of a creative solution here. So the first thing I'm going to do is I'm going to get the integral from 0 to infinity e to the negative x squared dx. I'm going to split that into the integral from 0 to 1 plus the integral from 1 to infinity. Okay. And I'm going to look at this in pieces now. So the first piece and then the second piece and try to see if I can show that these are convergent. Now the first integral from 0 to 1 of e to the negative x squared dx, this one is obviously convergent. Okay? There's no way around that. So the first integral is clearly convergent, okay, or I should say finite. Okay, the first one is finite. So if we can find that the other one is finite as well, or convergent, then that gives us that the whole thing is. Okay, so for the second integral, we have to do a little bit of comparing here. So we're dealing with x greater than or equal to 1. So when x is greater than or equal to 1, hopefully we can all agree that x squared is greater than or equal to x. Right? I mean, you could even just picture multiplying both sides of that by x to get that result. Okay, but when x is bigger than or equal to 1, x squared is bigger than or equal to x. So negative x squared is less than or equal to negative x. Right? Because if you multiply by negative 1 to an inequality, you flip the sign. So thus, if we raised both sides into the power of an e, the inequality would still hold. So e to the negative x squared would be less than or equal to e to the negative x. Okay, and I actually want to show you guys the graphs of these. Let me pull up Desmos. So we have e to the negative x and e to the negative x squared. So here are the graphs. And remember, we split these at 1. So let me just dot that. Okay, so from 0 to 1, right, we do have e to the negative x squared is actually larger from 0 to 1. However, we know that this area is finite under here. Right? You can clearly see, right? It's going from 0 to 1. That is finite. But as we go from 1 onward, e to the negative x is on top this entire way. Okay, so that function is larger. So what we can do now is work with the easier function, e to the negative x, and if that converges, then certainly the smaller function of e to the negative x squared must also converge. Okay, so if the area under this one is finite, then the area under this one must also be finite. And that's the argument that we're going to be making. Okay, so we have our integral from 1 to infinity of e to the negative x dx. So that's the limit as t approaches infinity of the integral from 1 to t of e to the negative x dx. Okay, go ahead and evaluate that. We get negative e to the negative x evaluated from 1 to t. So we have limit as t approaches infinity of, we get negative e to the negative t minus negative e to the negative 1. So that's going to become plus. And it's e to the negative 1, but I'm just going to write it as 1 over e, because those are the same thing. And that way I can get rid of a negative power. Okay. And so then notice what happens. As t goes to infinity, this value is going to head towards 0. Does everybody see why that is? Because this is going to be getting more and more negative. So it'll be e to the negative 100, e to the negative 1,000, e to the negative 1,000,000. So that's going to become 1 over e to the t. And as t gets bigger and bigger, the denominator is going to get larger, so the whole thing is going to get smaller. And it's going to head towards 0, using similar arguments we made earlier in this section. So the value of the first part is going to go to 0, which means we're just going to be left with 1 over e. And 1 over e is just a number. This is clearly finite, okay, which means that it converges. So it converges. And now we can go ahead and make our argument, because we know that this first part converges, right, is finite. We know that the second part, now we know it converges, right, because something bigger than it converges on this interval. Okay, so let's go ahead and state our argument. So thus, by the comparison theorem, since, I'll fill in the e's in just a second. Since e to the negative x squared is less than or equal to e to the negative x, for x less than or equal to 1, and the integral converges, then our integral from 1 to infinity is going to converge as well. Sorry, I know I'm leaving a lot of blanks in there. I'll go ahead and fill this in right now. Okay, so we have e to the negative x squared being less than or equal to e to the negative x for x less than or equal to 1, and the integral from 1 to infinity of e to the negative x dx converges. Then the integral from 1 to infinity of e to the negative x squared dx converges as well. Okay, so again, by the comparison theorem, since this function is smaller than this one on x greater than or less than or equal to 1, and the bigger one converges, then the smaller one converges. Okay, so therefore, since we know that the piece from 0 to 1 is finite, the piece from 1 to infinity converges, we know the integral from 0 to infinity of e to the negative x squared dx converges. All right. And then one more example for this section. The question is the integral from 1 to infinity of 1 plus e to the negative x all over x dx convergent or divergent? So when we're dealing with the comparison theorem, we need to compare. So we're going to look at 1 plus e to the negative x over x. Now the e to the negative x, that is going to be a positive value, okay, because we're going from 1 to infinity. So we're going to be adding up some value to 1, which means that this function must be bigger than 1 over x when x is greater than 1. Right, so hopefully everybody sees that. So because this value will always be positive, it'll be small, but it'll be positive, being added onto 1 above this x, that's going to be bigger than 1 over x anytime we have an x value greater than 1. So since this function is is bigger than this one, is bigger than 1 over x, and we found earlier in the section the integral from 1 to infinity of 1 over x dx diverges. So again, this function's bigger than 1 over x. The integral of 1 over x diverges. Then, by the comparison theorem, the integral of this function it must diverge as well.